let's get started. Our last lecture of the semester. All right, homework 9 is due right now. There's a pile up there. If you haven't turned it in, get that turned in like now. Exam on Monday, starting at 10:15. One thing I will go ahead and tell you, and I think that you all found this was the case last semester, but same deal. We're given 2 hours for the exam, but honestly, this is just an exam like any other, so it's not like it's twice as long. It's not like there's 6 problems on the exam. There's just the same, it's pretty much the same format as it always is. I've given this exam, a very similar one, a number of times. I've never had a student who had an issue with time on this one, especially given the content, because this stuff really isn't that long. I mean, like development length problems, column problems, they're not long problems. They're pretty straightforward. One thing before I get into the review, course eval. Now, I'm going to let you upload proof of completion between now and exam time, but it closes tonight, okay? It closes tonight at midnight. And to date, there's 7 of you that haven't done it, okay? It's free points, so if you haven't done it yet, do it. Again, you can say I'm the worst professor ever, but if you do it, that's like pretty much like when you work out all the math, it's basically adding a point to the end of your, at the end. So like if you have an 88, it'll bring it up to about an 89. It's 10 extra homework points. That's pretty much how it washes out at the end. Let's get into the exam review. One other thing I'll mention, I posted the solution for homework 9. It should be up now. Like it was set to turn on at 10 a.m., so it should be available right now. Let's talk about the exam. Oh, wrong one. Okay. All right, you all know the drill. It's closed book, closed notes. You're allowed to utilize a calculator and a formula sheet. Put whatever you want on the formula sheet except for worked out examples. Note that any design guides, beam column charts, tabular data, anything like that, all that stuff will be provided. So please do not occupy your formula sheet with, like rebar charts with all that. Don't waste your space on your formula sheet. Put other stuff on there. We are starting the exam at 10:15 a.m. sharp, but you know my rule. If everybody's here, and I mean every single one of you, if you are here, we will start the exam early, but that means everybody's got to be here. I'll have scratch paper, I'll have staplers, y'all know the drill. The coverage is lecture notes 12 through 14, homeworks, bless you, homeworks 8 through 9, so development length columns and beam columns. So here's the deal. Be able to, for development length, make sure that you can identify all the parameters that affect development length, so you know what's going on with bar coding, with the bar size, the bar location, all those adjustment factors. Make sure you can compute the development length for straight bars and hooks, and that you know how to do all the appropriate reductions and all that. For columns, make sure you can analyze and design, bless you, make sure you can analyze and design square and circular columns, and that you can assess all the detailing requirements, the spiral spacing, tie spacing, all that stuff. Beam columns, make sure that you can use interaction charts to size beam columns. That's basically it. Here's some provisions. So the development length for straight bar equation, you can reduce the development length if more steel is provided than necessary. You all know how to do that. You've got your reinforcement location factor, your bar coding factor, your reinforcement size factor. Remember that this quantity has to be less than or equal to 1.7. I don't have it on this slide, but also remember that this fraction here on the denominator has to be less than or equal to what? 2.5. So these come straight from the lecture notes on what is the bar size factor, the reinforcement location factor, the epoxy coating factor. Oh, it's right here. Never mind. So here's the limits on the denominator. I think I probably put this on a separate slide because I like the little image that actually defined what CB was. So CB is the minimum of those three distances, either the edge distance, the top distance, or the half the center to center spacing. Your KTR, your transverse reinforcement index, 40 times the area of the transverse reinforcement divided by S times N. Remember, the transverse reinforcement, that's basically just your shear reinforcement. S is the center to center spacing, so basically your stirrup spacing. And N is the number of bars in a single layer. Remember, all the single layers, all the single layers. Laughed at that one, but not the Thanos one. And the movie came out today. I figured the Thanos one would be a good one. The development length expression for hooks. So here's the expression. All the factors that are included, which is basically the epoxy coating factor, is the same. You can also reduce that appropriately. Cover factor and confinement factor, all on one slide. I know there's a lot more slides with this exam review, but it's really just because there's a lot of pictures and a lot of code provision stuff that you can pretty easily transcribe onto an 8.5 by 11. Axially loaded members. So there's your fundamental equation for computing the design capacity, the VPN for an axially loaded column. So you've got tied columns and spiral columns. Remember, for tied and spiral columns, the phi and the alpha value changes. Let's see. I also have listed all the cast in place, or the requirements for cast in place columns, so that your rho has to be between 1% and 8%. You got to use at least 4 bars for tied columns and 6 bars for spiral columns. Let's see. This just really, just copy and paste from the lecture notes. The additional requirements for tied columns, and then additional requirements for spiral columns here in that box. Here's your spiral reinforcement. This is the amount required, and this is the amount that you've actually provided. Column design equations, and then the procedure for beam column design. And that is your final. Floor is yours. Yes, sir. Sure. Okay. So for this one right here, the cover factor, so right now the cover factor is the psi sub c, and it's going to be 1 except in the following cases. If you have cover behind the hook that's greater than or equal to 2 inches, so that's what I'm talking about right here. So that's this distance right there. That's this one. So this is a 90-degree hook, and that cover behind the hook has to be greater than or equal to 2 inches. Or you can meet this one right here. So if you have a hook that's number 11 or smaller, the side cover has to be greater than or equal to 2.5 inches. So what I mean by that is, if you ever have a hook and the bars are number 11 or smaller, so if you got like a number 8 bar or what have you, and the side cover is 3 inches, then you can take this value to be 0.7. And let me pull up an example to sort of illustrate that. Let me pull up, I think I have the lecture notes right here. We got a lot of slides, so bear with me. Right here. Okay, this is a perfect example. Man, that was good. Okay, so here's looking at this problem right here. Now the side cover is talking about the distance from here. Oh no. Come on. Give me 1 sec. My pen's running out of ink. Okay. Okay, so the side cover is talking about that distance right there. Okay? So in order to use a cover factor of 0.7, that distance has to be greater than or equal to 2.5 inches. My question for you, is it greater than 2.5 inches? No. It's less than, because it's 2.5 inches to the minus the diameter, exactly. So one way that we could possibly get a cover factor of 0.7 is take those bars and just scooch them in a little bit. Do you see what I mean? So if this was, I don't know, let's say this was 3.5 inches, then you know you'd be fine, so your cover factor would be 0.7. But because we're just a little bit on that side, we're not quite there. Because for 90-degree hooks, when you're yanking them, they can do that. You see what I mean? So you kind of need enough of a buffer back here. So did the hand thing work out? Do you like that? All right. So everybody good on that? Yes. Yes. That is correct. These kids playing pranks on these pens, man, I'm telling you. I know things. I hear stories and things about certain classes that also occupy this room. Oh, everybody's like, oh, we didn't think Dr. Mike knew about that. Oh, yeah. Uh-huh, yeah. I'm now lost, yeah. So. All right. Any other questions? I mean, this is your time, for the final. I really want it to be valuable. So, yes, sir.
Quick question. When we're designing square columns, we have to have an even number of bars, and spiral can be odd if need be.
So the question was for square columns, do we have to have an even number of bars? And as for circular columns, we can use whatever. Let me answer it this way. For circular columns, yes, you can pretty much use whatever and just evenly space it. More often than not, that's going to be fine. I am very hesitant to use the word have to, okay? Because you don't have to use an even number of bars for square columns. It usually makes sense to use an even number of bars. And for the purposes of the exam, use an even number of bars. So, but I'm hesitant to use that term, I just, like if you're designing like this super massive column and you could do it with 5 number 18s or 6 number 18s, I'd almost say figure out a way to do 5 number 18s, because have you seen a number 18 bar? It's huge. It's like that. We're talking about a piece of rebar that's like that. It's huge. Yes. Remember. Let's also keep in mind, when you're designing circular columns, you're usually trying to take advantage of spiral reinforcement. And give me a sec. Spiral and ACI specifically states that if you're wanting to take advantage of spiral reinforcement, you have to have at least 6 bars. So remember that. So. From a capacity standpoint, yeah, I guess you could, but again, imagine just a number 18 just dangling in the air. Now, let me also qualify this by adding one other point. We're not talking about piles, okay? We're not talking about a pile that's laterally supported and you're taking that bar and lowering it into the ground. That is a little bit of a different story, okay? But if you're needing a number 18 bar for a pile, that's usually a pretty interesting pile, and we'll move on from there. It's just the end of the semester, right? Y'all are done, or you're cured, like, because it's concrete. But still, the crickets on the Thanos one. I'm just wow. Yeah, no, us engineering students who have all this homework, we haven't had time to go see the movie.
No, I just stayed up later and did homework.
Field trip. Amber told us it would be okay the other day. Does that count? Yeah. She gave us Jolly Ranchers and told us it would be
Wait, hold on.
Actually, she threw it.
Wait.
It was more of like Yankees.
Hold on. What's going on? Like,
We were sitting in the lobby. Everyone looked like they were dying. She walked by, looked at us, didn't say anything, came back, and was like, "It'll be okay." And then she came back a third time with candy and just went and like threw it over the partition of the chairs.
so it doesn't have anything to do with the Avengers or anything. Just.
We're just dead. That's basically it.
Yeah. Okay. Jolly Ranchers are good. I like Jolly Ranchers. What? What fail? What? Let me say this. I used to be rather picky and used to be, sort of like I only, ate green Jolly Ranchers, but now I'll just eat any. I like Jolly Ranchers. I'll say this. If I had to pick a favorite, though, green's not on the top of the list anymore. It was, but it's just not now.
You're one of those watermelon people now, aren't you?
Watermelon are pretty good. Game changer. This is why people hit the subscribe button and the notify bell.
Writing a book of engineering puns, and they're just taking all of your.
Senior design project, assessment of Jolly Ranchers as a course aggregate. When we broke the cylinder, it was like a big rainbow explosion. Boom. Oh, goodness.
We could use the concrete cylinders. Put the candy materials, and then we have like this giant Jolly Rancher.
Just melt all the Jolly Ranchers right into it.
Why don't we talk about this?
You might be onto something. All right, back to the exam. Let's talk about development length columns and beam columns. Any questions on that? This is your last chance to ask.
What was your second slide with the lecture notes and the homework 8 and 9?
12 through 14, I think it was. Because that's the development length, the column, and then the beam column one. Because the previous exam was shear deflection, and then we stopped from there. Hold on. Sorry, that was awesome. Usually, I'll go ahead and say this, usually it is a little bit of a wash, and it's mostly like units or calculation errors. In all honesty, it really is. But let me also say this, the conceptual problems tend to get people more than the computational ones. That's really where the divide is. I can't believe that was said to you. I'm just...
It's fantastic because I was like, well, you're kind of not wrong, but...
Confidence.
You know, actually, I might do.
Okay, all right. Back to concrete. But did that answer your question? I mean, as best I can. You also have to understand, I haven't graded my last, reinforced concrete design final. It was a year ago. So it's been a while. But here's the thing. But here's the thing. It's a lot easier to just write a 0. It's less pen strokes. Then everybody says, we just do the check mark, but there's no numbers associated with that. We're engineers. Tell you what, I'll get sunshine stickers and then stormy cloud stickers. It was like my first test in graduate school. When I got the grade or the test back, it didn't have a number on it on the grade. We're like, so how did we do? We all got them back and they didn't have grades on them, so we went. And everybody sat there for about 20 minutes for somebody to raise their hand and say, we don't even know how we did. And we went, oh, whoops, give them back. All right. Okay, questions, keep them coming. Anything else? Anything you can think of?
How hard do we have to swing a sledgehammer to break the concrete?
I'm gonna go with not that. I broke a piece off with my bare hands.
Any other questions? All right, before we leave, hold on. Are you good? Is he good?
Yeah, you better be.
Are they good? Good.
You start slacking in this area.
Well, what happens is Mr. Farley's staring at his laptop and he's it's all here. That's what it is. All right. Okay. So before we close it, this is my fourth time doing reinforced concrete design. So yeah, it's been fun. I think that this class is probably a lot different than a course where it's a lot of just differential equations and vectors and stuff like that. This is, I think I told you all back in structural analysis, I said, when you take this class, it's going to be a lot different. It's not going to be moment is 250 foot kips. It's going to be, here's the size of the beam with 8 number 6s and so on and so forth. So hopefully I think that this is this course has been a welcome refresher from a lot of the classes that you've had before, but B, I hope that you found that this class is pretty valuable in terms of applicable real world experience. This is what civil engineers do. What we do in here. This is about as real world civil engineering as we can get in a classroom without going down and actually getting some plywood and 2x4s and actually forming up some concrete beams. This is reinforced concrete design. I hope that you all have learned something. I think you have. I think you've had a good amount of material thrown at you. I hope you've had fun. And for most of the people in this room, you get to have me again next semester for senior design, for the senior design experience, which begins in the fall. So I'm teaching senior design. How many of you are taking co-op next semester as well? Okay, so.
What about engineering, like 103?
103. I have had students taking that and senior design at the same times.
Really tight.
Before I close, one final thing. This class is always a blast for me to teach. I mean, I just love teaching, but this is where I think you get to take all the stuff that you've learned for the past couple years and really start to see it all tied together. I mean, we're taking structural. That was a good one. That was a good one. All right. Don't study too hard. Oh, I'm redoing this exam now. I'm making it really difficult. Well, you've been studying this stuff all semester. I mean, what's 2 days going to get you? hold on. Now, everybody's getting all worried. Hold on. No, we had to change things. Tell me what's going on with this right here. When did I tell y'all about that? Back in like January. So, see? All right. You put in PSI, you get out PSI. All right, guys. This has been a blast. It's been a lot of fun. I will see you all on Monday. Don't forget your course evals. I'll see you Monday at 10:15. All right.